If you don't, then that's fine too, because I'm going to teach it as if, you know, nobody's seen it before. And so, you know, for those who have seen it, it could be kind of on the boring side. But one thing that you'll find is the notation differences between Calc 3 and physics, or even linear algebra, is enough to make you kind of want to go back and say, all right, let me listen to what this guy has to say, because he's doing it in a different way. And I'll preface everything I'm about to say by saying the answer is no. So when the question is, can I do this using the method I learned in meh, the answer is no. All right, because and it's not because I'm particular or selfish when it comes to the content that I'm teaching. It has more to do with the fact that generally the methods that you learn in a physics class don't involve calculus. And I was mentioning before that if you don't have a calculus solution, then I can't give you credit for having solved the calculus problem. All right, so that's something to keep in mind. All right, so you may want to do it using a formula that you learned in the physics class, and that's wonderful. I would say use those formulas to check your work rather than to do your work. All right. So the vector is quantity that has both magnitude and direction. All right. It's kind of a vague comment, but at this point we're just learning about what it looks like graphically and geometrically. So it really doesn't have to mean too much right now. Sketch a vector in the plane from initial point 1, 1 to point 4, 5. So you just think back to the GeoGebra tech assignment, and you can see that we've kind of already tackled a lot of this, right? And that was kind of the point. So 1, 1 is point P, and 4, 5, so 2, 3, 4, and then 2, 3, 4, 5. So that would be my point. I'm pretty sure it's 4, 5, Q, at location 4, 5. So this is a line segment, and it's really nothing more than a line segment right now. But what we're going to do is we're going to pin one of the coordinates that make up this line segment. We're going to pin that to the origin. Okay? So what I'm going to do is I'm going to take this point P, I'll highlight it in yellow, and I'm going to shift it to the left 1 unit and down 1 unit. Right? And correspondingly, I'm going to shift Q that same in that same fashion. So left 1 unit, down 1 unit. Right? And we get 2 fresh new points. But those 2 fresh new points are going to have the same orientation. Well, if I drew it correctly, they would. They're going to have the same orientation and the same length as the original line segment. Right? What we do is we indicate that with a little arrow, and we end up with what's known as a vector. Right? Now, this is a messy diagram, so what I tend to do is just kind of strip it down, redraw it, so that it doesn't have all the extra fluff on it. But I needed to show the actual movements first. That was weird. I was supposed to autocorrect. So I have this. So what I do is I just kind of grab this guy here and shunt it over here. All right. So what we want to do is we want to take note of where the endpoint is of this new ray. All right. So this endpoint here. Now we're going to designate this whole thing as vector PQ. All right, little arrow on the top indicates that it's a vector, and the order of the letters are very important. It indicates the direction of the vector. It's going from P to Q. All right, now the coordinates of that particular point, well, originally it was 4, 5, but before it got shifted, so Q was 4, 5, then it got shifted to the left. So we moved it to the left 1 unit. Comma. It was at 5, and we shifted it down 1 unit. All right, so this gives us an ordered pair of 3, 4. But when we want to designate the vector, vector PQ is now written in component form with a little kind of a hard angular bracket, 3, 4. And what that is symbolic notation indicating that there is a vector that starts at the origin, as it should, and terminates at the point 3, 4. All right. There's a lot we can do with this, but for now we're just learning the skills. Right. So, you know, the rule below, component form of a vector, is really just detailing what I just showed you. Right. So we found the subtraction and the ones. It's like, are we always going to shift 1? No, we're shifting 1 because of the coordinates in P. That's 1, 1. In order to get P to the origin, I had to shift left 1 and down 1. But if I wanted to, if I had coordinates P were 2, 3, I'd shift left 3 and down, left 2, down 3. All right. So it's all dependent on that first point, how far you have to move in order to get you to the origin. Right. Whatever you do to the one, you do to the other, and that gives you the name of the vector. Right. Because it wouldn't make sense to say vector going from 0, 0 to 3, 4. Because all vectors are going to start at 0, 0. So it becomes part of the nomenclature. Right. So they express V with a vector initial point -2, -2, and a terminal point 1, 2. So we're calling this vector V, little arrow on the top. We take the terminal point, right, the X value, and subtract from it the initial point. So in both cases, we're subtracting off of -2. And we do that so that we don't actually have to write or draw out a diagram every time. Right. So we're looking at 3, 4 as a result of this computation, and that is our vector V. All right. A little definition here. Vectors are said to be equivalent vectors if they have the same magnitude and direction. All right. So you could, in theory, have 2 different vectors, but as long as when you put them in component form, they end up being the same, you're fine. So if I tell you that one vector goes from 1, 1 to 4, 5, and another vector goes from -2, -2 to 1, 2, well, fun fact, they both end up being 3, 4. So these are what are called equivalent vectors. Right? They're both 3, 4. They have the same magnitude, the same direction, and so therefore the same value. All right. I'm not really sure why I have so much space after the definition there. So I'll take that as a typo. That whole gap really should, I don't know why it's like that. Call it a formatting mistake, but I have no excuse other than that. So three types of operations we're going to focus on initially. We have addition, subtraction, and scalar multiplication of vectors. All right. So this is when you already know what the vectors are, how you can convert from one form to another has already been taken care of. So now it's a matter of like, if I have 2 separate vectors, if I want to add them together or multiply them together, what can I do? Here we're only focusing on addition, subtraction, multiplication, scalar multiplication specifically. So very simple for addition, subtraction. You just add the respective components. So for m plus p, I'm taking 5, -7, and adding to it -1, 3. So the 5 goes with the -1, the -7 goes with the 3. Right, so that's not too bad, not too bad at all. So you get 4, -4. But sometimes you have a combination of operations. So here we're looking at a 2 times m, 2 times vector m. So I'm looking at 2 triangular bracket 5, -7. I would also want to do 3 times vector n. So 3 triangular bracket, 0, 4. And then ultimately I'm going to add on p, but I don't really need to write, oh, I'm sorry, subtract p. So I don't really need to write it because it's going to be a subtraction step, but you can, because negative p is the same as negative 1p. So we'd be looking at 10, negative 14, 0, 12, 1, negative 3. And then it just becomes a matter of adding these up, and we'll have the result of the operation. Right. So we'd be looking at 11. And then negative 14 plus 12 is negative 2. Minus 3 is negative 5. So 11, negative 5. Right. So that's where I'm going to leave it for tonight. But I'll tell you that coming in next time, what we're going to do is talk about what this looks like graphically. Because, yeah, we can take vector u and add it to v, but what does that mean in terms of a physical movement, right? So there's more coming, but that's going to kind of get us going in the right direction. If you have time between now and next class, what I would recommend is that you just kind of look this over, the properties of vector addition and scalar multiplication, just because some of them are common sense, and then some of them are like, oh, where did that one come from? Okay, because I'm going to talk about this in detail next time, and so it's definitely worth your time. All right. So at this point, I'm going to end class, and so if you have any quick questions, because as you know, I got the next class coming in. If you have any quick questions, stick around. Otherwise, have a wonderful evening, and I'll see you on Wednesday.
Did you take a test, Professor?